Welcome to this course. This course is on momentum and mass transfer. We are going to look at, so this course consists of two parts. First part is momentum transfer. Second part is mass transfer. We will start with momentum transfer. If you are thinking about what momentum transfer is, we will look at what is momentum transfer as we go along. If you want to think about it as if it's course part on fluid flow. So a course that deals with flow of fluids, that's the first part, momentum transfer. You can think of it as flow of fluids. We will see why it is called as momentum transfer in due course of time. Today what we are going to do is look at various types of flow. So if you are dealing with flow of fluids, uh, think about various situations which involve flow of fluids. For example, one example you can think of is flow of air when you start a fan. That's a flow of fluid. Second, which is very much relevant just now, is flow of clouds and the moisture from the Arabian Sea or from the Bay of Bengal, which brings us this monsoon. That's flow of fluids arising out of differences of pressure in the environment. If you want to think of fluids, you can think of fluids, flow of fluids. Say, for example, when you are filling a bucket, or when you are trying to heat up some liquid. So, along with uh, motion of the fluid, you also have heat being transferred there. So, that we'll see slightly later on. When you are trying to mix something, you are mixing different components by making the fluids flow in a container or in a reactor or things like that. So one immediate assignment or one immediate thought for you is try to visualize or try to list out various situations in which flow of fluids is involved. You can come across many, and you can keep on listing them. We will see some examples in this course. Other situations that you can think of is, along with this flow of fluid, a lot of other useful things might be happening. You want to be, let's say you are spraying a perfume in this room and you want to mix that perfume in the room very quickly, so you switch on the fan, and then flow of the air makes this mixing happen very quickly. So although we are going to look at the flow of fluids in the first part, in the second part we are going to look at using that flow of fluids to make some mixing operation happen, or make heat transfer happen, or make mass transfer happen. In mass, in the sense that one component from making it go from one location to another location at a faster rate, or at a rate that we want to achieve. Uh, so this first part is primarily going to deal with flow of fluids. But remember, why we are dealing with flow of fluids is because we want to achieve something. Either flow of fluid itself is an objective, or mixing is an objective, or heat transfer is an objective. So for those, or making reactions happen, if you want to make, let's say, some reaction happen, you like to mix the reactant and the catalyst and effectively give heat, and then whatever heat is generated, you want to take that heat out, and you want to mix the product so that it is nicely homogeneously mixed. You can make it precipitate, things like that. So flow of fluids is required for doing many applications in as you're going to deal with in your second year, third year, and fourth year. So first part is very important. We are going to deal with the basic part first, dealing with the flow of fluids. Uh, throughout this series of lectures, you should have a pen and paper and calculator ready. Whenever there is a problem that is being displayed, you should pause the video, solve that problem yourself, and once you have got the solution, then you should go forward in the video. Let's start by looking at some of the uh, very common things which involve flow of fluids. what we are going to do is try to look at some videos in which some kind of flow of fluids will be involved. And what I would like you to do is to make a note of various things that you see, uh, and try to see what are the fundamental principles of fluid flow that you can think of. As we go along, we will talk about all these principles more and more. So let's start by looking at some of the videos. It's a simple video of mixing milk in a coffee. So you have poured the milk, and now what are you going to do? You're going to stir this milk inside the coffee using a spoon. So you see, we can see that again. Milk is poured. Now you see how the milk gets mixed very quickly within the coffee with the help of spoon. Right? Do this every day without realizing that there is motion of fluid involved in it. Some other example, if you would like to think, let's say mixing of coffee in a, or mixing of milk in a coffee. That was one example. Now think about mixing something very some other liquid. Let's say we are trying to mix paint in a bucket, and we are trying to mix one paint. Okay, so this is a bucket of white paint, and a red paint is poured, and with a wooden ruler or a handle, if you like, wooden stick, you are trying to mix the paint. You're trying to mix the red paint into the white paint. Now all along while you see this, try to uh, try to contrast this kind of mixing with what you saw when you were trying to mix coffee and when you're trying to mix milk in a coffee, and try to identify various different aspects that are involved when one is mixing paint, white paint, red paint into a white paint, or when one is mixing uh, coffee and milk. One of the things that you will think of, so pause the video, make a list of all the things that you think are responsible for this different behavior. One of the things that you would say is that mixing of coffee and milk happens very quickly, right? And you may say, because they are low viscosity liquids. You might have heard this word viscosity. Is a property of the material. All these kinds of words you would have heard, and you will simply say that, oh, milk, coffee, these are low viscosity liquids, therefore they mix very easily. Paint, on the other hand, is a highly viscous medium. Okay? So these words, so you may start using these words such as viscosity, and if I ask you to define what is viscosity, some of you may say viscosity is a resistance offered by the fluid. So just make a note of different things, make a note of different concepts that you know when you talk about motion of liquids, and we'll try to see all of these. We'll try to see what kind of mixing happens when you're mixing a red paint and a white paint. Say for example, if I look at this video, if I pause this video, let me go back a little bit. Okay, now if you start this video and I'll pause it at some particular place, and then we'll talk about it. Here, do you see that there are red regions, there are white regions, and there are bands that start appearing, and somewhere else later on it is even more visible. You see, now this is a red paint, this is a white paint, and the mixing happens by mixing of these different layers of paint. So as if the red paint and the white paint are being broken up into different layers, and then these different layers are mixing with each other, or the paint is mixing across these different layers. So that's one kind of mixing that happens. Now contrast this with the mixing of coffee. Now do you see layers here? When this coffee and milk is being mixed, do we see layer? Yeah, of course, there's one milk layer here and one coffee layer here. But now when this mixing is happening, maybe I will just take this back a little bit. When this mixing is happening, do you see layer like pattern that you saw when paint was being mixed? No, you don't. So this kind of mixing where layers don't happen is just different kind of mixing. A different kind of mixing phenomena is happening, different kind of fluid flow phenomena is happening, which is responsible for mixing. The next word that you might have heard is that laminar flow and turbulent flow, right? So here is one video. So imagine that there is a pipe here. Let me just pause this video. Yeah, so imagine that there is a pipe here. There is a pipe and flow is happening from left to right, as you see. And just to make the flow visible, blue colored ink is put in some places, and then you can see that these layers of blue ink, they move along without mixing much with each other. Say for example, this layer, they are not mixing significantly with each other, right? You see this? So this also is a layer like phenomena, and you might have heard somewhere that this layer like flow of fluids we call as laminar flow. Okay, but we will see as we go along more in detail what we mean by laminar flow, how to characterize that, how to calculate that, and how to make calculations for that. The other kind of thing that you might have seen is something like this. So there is a pipe here. Now again there is a dye that is put in, blue dye that is put in, but now you see that this dye does not move like a layer. It moves all across the pipe in a random fluctuating manner. You see, it has spread, so to say, across the different regions of the pipe, and we call this as turbulent flow. So again, you might have heard these names: layer like motion of the fluid, one layer sliding over another layer, laminar flow, or layers which are not well defined, they are sort of mixed, and then that very random process, very violent, so to say, process uh, happens. We call this as a turbulent flow. So we will see in this course how to characterize laminar flow, how to characterize turbulent flow, and and how do we make calculations based on whether flow is laminar, whether flow is turbulent, and so on and so forth. Some other mixing processes you might have seen earlier. Okay, let's see this. This is a process wherein there is a soup, and then there is a oil layer on this soup, and then this oil layer is mixed with the with the spoon. So you see, highly agitated fluid, mixing happens very quickly. We would say this is turbulent flow. Another characteristic of turbulent flow you will see in another video. Okay? So imagine again, this is that soup and an oil layer on that soup, and you see when these spoon has moved through this soup layer, you see these vortices, these circular structures that appear, and these circular structures are called as vortices. And you see these vortices, they create a lot of mixing. and these vortices persist for a long time. So for example, these vortices, these are generated, see here, these are these vortices that happen, they play a part everywhere. So for example, this is one video where there is a chimney and there is a smoke coming out of that chimney. You see these circular patterns that happen, these are called as vortices, and this is a very important phenomena which causes mixing of these effluents with the atmosphere. And you will see in your semester 6 course how the atmospheric conditions of temperature and pressure affect the dispersion of pollutants from these chimneys. So these are called as atmospheric dispersion. And you see these vortices that are there at the edge, and you don't see a nice regular structure, you see a structure which is changing with time, very dynamic. So that's one more characteristic of turbulent phenomena, that it is very dynamic. And in a time average sense, so if you take an average over a long period of time, then you will see that dispersion is nicely happening. But here now you can see these vortices and these circular motions much better, in much more clearer manner. One more place where these vortices play a very important role. I'll just show you the video first, then we'll talk about it. So this is a very dramatic visualization of vortices that happen. So imagine there are two, just for visualization, there are two smoke sort of plumes that are sent, and then an aircraft will go through this plume, and you will see that circular motion is generated, right? You see this circular motion, that's like a cyclonic circulation that we have in weather, and cyclonic storms that come and so on and so forth. It's the same kind of circular motion, right? Both these are generated. So these are called as wingtip vortices or wingtip vortex, and then these play a very crucial role in how the aircraft moves, how much energy is required, how much fuel needs to be consumed, and so on and so forth. The next thing that we will look at is some more dramatic visualization of various kinds of experiments, various kinds of flow visualization that people have done for different kinds of phenomena. Here is one more video related to uh, flow of water or flow of fluid in pipes. So you might have heard about this name Reynolds number, and you see these are 6 different pipes, 1 2 3 4 5 6, and you will see that how this mixing of this pink dye happens in these pipes when the flow rates are different in each of these pipes. So you see at large Reynolds number it is nicely mixed, called as turbulent flow. At low Reynolds number it is moving like layer, right? So you see here it is moving like a layer, It is not mixing very well. So compare and contrast this extreme left video, Reynolds number 1600 with Reynolds number 10,500. And you see somewhere in between this 4,200, sometimes it is layer like, sometimes it is like this mixing behavior. So this is called as laminar flow, this is called as turbulent flow, and some of these are called as transition flows. Sometimes it is layer like, sometimes it is behaving like this. This happens because velocity of the fluid is different in different pipes, and that makes the flow either laminar, layer like, or turbulent, which intense mixing, vortices, random nature, and so on and so forth. So these are the two extreme situations that we are going to look at, laminar flow, turbulent flow. And we are going to look at both these in a lot more detail and do a lot more calculations as we go along in this course. Flow of fluids is very common. You can find out flow of fluids everywhere. Here is one dramatic video. So this person, this is just the thermal convection. This temperature of a human body is 37. Outside, if it is something like 25, 27, there's a natural convection that is set up. And when this person breathes, you can see this plume of air that comes out at a high velocity. It's like a jet of high velocity air. This technique is called as shadowgraphy. You can find out more details in your from internet, but just shows you what kind of intense mixing happens even when we start, even when we are just breathing. Now imagine that it is very important in today's context of coronavirus that you see just the breathing plume has reached up to here. When we say that virus is transmitted by just the exhaled breath entering droplets, you can see just by simple breathing what kind of velocities are generated, and if these virus particles are tiny, how they will get transmitted from in the near vicinity of this person. That's why we say social distancing and so on and so forth, that you maintain some distance so that we can prevent the transmission. You see, just the process of normal breathing has generated a plume like this. So if there are entrained droplets, they will get carried away and then the next person can get infected. So this is phenomena of fluid flow is prevalent everywhere. When we breathe, okay, these are some simulations, but when we breathe in, so this is our windpipe, and then that branches into two parts. Let me just take this back a little bit. Yeah, so that branches into two parts and goes to the two lungs. And you see these colors or contours are of velocity. So blue region is a low velocity region, red region is the high velocity region. And you will see when we breathe in and breathe out, how these velocities change. So we are breathing out now, and we are breathing in and out. Right? And in and out, breathing in and breathing out. So these are the kind of velocity fields or velocity patterns that are generated inside our body when the air goes from our nose and mouth into our lungs. You see, the profile is not uniform. Profile is tilted on one side. So these kinds of calculations are very important. So if you think about people with asthma, they take this medicine through inhaler. And these kinds of calculations become important when you think about patients with asthma. They take this medicine through the inhaler. So they put it in their mouth and then they press and then they breathe simultaneously. So the whole medicine goes into their lungs where it gives the cure. And this kind of flow pattern, this kind of study is required to see how much of the medicine reaches the target area of the lungs how much of it remains in the mouth, and so on and so forth. And that's how these inhalers are designed. So fluid flow is required for even things like delivering drugs and various kinds of applications. One more thing that is very different about laminar flow and turbulent flow, I will show you now. Right, so here are two cylinders. This is one inner cylinder and this is an outer cylinder, and some red or black colored dye is put in here just to make the flow, just to visualize the flow that happens. And this outer cylinder is going to be turned in the anti-clockwise direction. You will see this outer cylinder moving in an anti-clockwise direction, and because of that, the fluid, this inner cylinder is stationary. The fluid near the inner cylinder is not moving, or is moving very slightly, whereas the fluid near the outer cylinder is moving at a much larger velocity, and therefore the fluid that is in between this region is distorted, and that distortion you are able to see by the distortion of these letters. So you see it getting distorted. Now what's going to happen is this rotation is going to be reversed, and you see what happens to the letters that are formed. See, now the direction of rotation is reversed. It is now rotating in the clockwise direction. It has come back to its original shape. It has come back to its original location. It has come back to its original location. But what has happened to these letters? The letters are now distorted. What does that mean? That means that the fluid that was there initially or at one location has now displaced, has mixed with the other fluid. It is no longer coming back to that same location. That's a very characteristic of turbulent phenomenon, turbulent flow. Mixing happens. Now you see another video. Now again, inner cylinder, outer cylinder, just the fluid is different. Now again this outer cylinder is going to be rotated. You will see the deformation. So outer cylinder starts rotating. Again, the fluid in this region near the inner cylinder is moving very slowly. Fluid in the outer region near this outer cylinder is moving much faster, and you will see that this causes a deformation or a distortion in the fluid, and you can visualize that by the distortion of these letters. So you see letters are getting distorted more and more. Now the situation is reversed. Now the outer cylinder is going to be rotated in the reverse direction, clockwise direction back, to bring this part back to its original location. Now you see what has happened to these letters. They have almost come back to their original location. That's why the letters are appearing again, and we can read them again. They are appearing almost in the same manner, almost what we started with. So that's one more characteristic of laminar flow, that the flows are reversible. If you reverse the direction, entire sequence or entire path traced by the fluid will get reversed, and the fluid which we started with at one particular location, or a part of the fluid which we started at one particular location, will come back to its original location. The flow of fluids is also common in our day-to-day phenomena. So for example, if you are having a car and you're traveling at, let's say, 60 kilometers per hour, uh, that's equivalent to saying that car is stationary and air is going past that car in the opposite direction at 60 kilometers per hour. And if you put some smoke particles, say here, you can visualize how these travel, and these lines are called as streamlines. The lines uh, or the path that the fluid particles take around this car. Now you see there is a jeep here and there is a sports car here, and now you see how the fluid streamlines take a very dramatic behavior when we talk about jeep or when we talk about a sports car. And you see that the region of fluid that is affected by the presence of this car, by the presence of this car in this airstream, is much less here, whereas it is much more significant here. Now this is something we call as drag. This is something that we will spend a lot of time on in this course, and how this drag makes a difference in our day-to-day in our day-to-day life. Not just that, if you think about uh, any any game, any sports which involves all these are applicable. So imagine that there's a tennis ball or a, or a table tennis ball, and that ball is being hit, and now this ball is hit. It is as if you can visualize that as if the ball is stationary and air is flowing past that ball, and now you see the flow behind this ball is very different depending on whether the don't worry about the names turbulent boundary layer and laminar boundary layer, but just try to see the differences just now, and you see that these situations are very different. And same thing happens for different balls. So this one we saw, yeah, let's see this one. Yeah, you see these kinds of things are very important. Now this kind of behavior, you see this air pattern behind this ball is fluctuating, it is not steady. You see it is fluctuating, and that leads to forces on this ball, and if these forces are very large, they can even create problems for this object that is there. One very dramatic example is this. You see, this is a bridge, wooden, concrete and steel bridge, and there is a cross flow wind that causes this unsteady flow structure behind this bridge, and those unsteady structure leads to forces on that bridge, and then that bridge, you see how dramatically and how violently this whole concrete cement bridge is uh, vibrating like a rubber band, and finally it led to the collapse of that bridge. This is just because of the flow of wind at high pressure, at high velocities around the bridge, perpendicular to the bridge. So bridge, you see bridge, this is the direction of the bridge, this is the direction of the bridge, the wind is coming perpendicular to this to these two towers, and that's what causes this motion. Sometimes it's not just these dramatic visualizations that are there, they can be there in even some very ordinary places. So here is one example. You see that, then we'll talk about it. A drop of milk being put in a coffee cup. You might think, oh, what an ordinary situation. We do this every day. Look closer and look at slow motion video. A drop has splashed. Now, well, you might think, oh, drop has splashed and a crown is formed. Now you see something even more dramatic. A jet of milk is generated upwards, and then these satellite drops are formed upwards. You see these satellite drops. this jet is formed upwards and these satellite drops are formed from this jet. See, we go forward slightly. A satellite drop has formed by breaking of this neck. You see how, what is the distance over which, this is the distance over which this jet is formed. Significant distance when you think about size of the drop. So drop may be say less than 1 millimeter, and this is several millimeters. So a drop is ejected at a distance of several millimeters. Just a simple action of dropping one drop of milk in a cup of coffee. All these satellite drops are now falling down. Same thing happens. So if milk drop is dropped on another drop of bowl of milk, again same crowning happens and a secondary jet is formed which ejects. A drop is formed by necking. A neck develops because of surface tension, and then this drop is formed. So it's an so flow of fluids is an everyday phenomena, but the situation can be very dramatic, very remarkable. Let's take some more videos. Sometimes you can use it for fun as well. You can use it for fun as well. So imagine, so this is a grating and you see this person is floating. These persons are not floating, but you see this person is floating in the air. So just the two, both of them may have the same weight, same size. One is floating, one is not floating. Okay. So you see the orientation also makes a difference when it comes to flow of fluids around different objects. Okay. So you see this person is floating in the air. We are using it for fun, having fun. People are having fun. Talked about laminar flow, turbulent flow. Sometimes fluids don't behave in a very nice way, and that can lead to some dramatic effects. Okay, I'll just show you some videos on that. So here is one video. Let's just see right from the start. So there is a blue colored liquid, there is a syringe, and this person is pulling the syringe, pulling the plunger so as to fill this syringe with the blue liquid. Very ordinary phenomena, you might think. Now you see what happens. Now you see this syringe is no longer dipping inside the liquid, and still when this is being pulled, liquid comes from the outside into this syringe. See, now see how far away that syringe is from the fluid. It is not dipping inside the fluid. Fluid is climbing inside the syringe. Does this happen with water? Obviously not. Okay. So these are some characteristic features of the fluid, characteristic properties of the fluid, which makes these kinds of things happen. Another behavior you might see. So imagine that this is some red liquid, and so this is some red liquid, and there is a stirrer here. So just a rod, and this rod is rotating. What you would expect if it was a water? What would you expect? You would expect a vortex to form, right? Now you see what happens. Instead of a vortex being formed, an opposite of a vortex is forming. The liquid is actually climbing, sticking and climbing up along the wall, along the rod. very famous experiment. This effect is called as Weisenberg effect, rod climbing, if you like. So just by changing the fluid, situation can go from a vortex like a water to a rod climbing behavior, Weisenberg effect. So these are some very special properties of fluid. One more very dramatic video I would like to show, then we will talk about it. So here a swimming pool full of this liquid is created. See, so this is swimming pool, small swimming pool full of liquid, and now you see what happens. If this was water, what do you think will happen to this person? Just fall down, fall inside. Now you see what happens. This person is as if walking on water. See, another person, even an old person, young person. People are walking on water. So a small child, well, the small child could not walk on it. We'll talk about the reasons why this happens. And you see, it is a fluid. It is not that there is some different material in it's a different material, but you will see that this is a fluid. This boy is sinking in this fluid, and then these people will dive inside and then bring that boy outside. It's a fluid, right? So fluids behave in a very dramatic variety of behavior, and we use all this behavior of different fluids to behave in different way: laminar flow, turbulent flow, rod climbing, walking on water, and so on and so forth. So many different phenomena of flow of fluids we utilize in our day-to-day life. You won't even realize that these are so commonly used, so common phenomena, that you might just take them for granted, but behind all these phenomena is a great science of fluid flow, momentum transfer, if you like. And that's what we are going to investigate in our course, and we're going to have look at, we are not going to be limited to some small area. We're going to look at all these aspects, all these kinds of different things that I showed you just now, and we are going to look at the mathematics behind it, the physics behind it. We are going to try to calculate, and we are going to see how to utilize all this. So that's what is coming in the first part of the course. What I would like you to do now is make a summary of different things that we have talked about in this roughly 45 minutes or so. What you have seen in different videos, what phenomena have you seen, and I gave you some pointers about what happens in a laminar flow, what happens in a turbulent flow. I would like you to write them down on a piece of in your notebooks, and at the end of the semester revisit this first page of the notebook and see that we have covered all these aspects. If you don't cover all these aspects, you tell me, and we will talk about them, and we will cover those aspects. So here is the homework for you now. Write down all the things that you saw, different things that you saw, different properties that I told you about laminar flow and turbulent flow. So pause the video, make notes for yourself, and then only go forward in this video. First thing that we saw was mixing, and how this mixing is different. Let me just increase the size of the font. Yeah. Mixing, and when we saw coffee, coffee versus paint, right? How mixing behavior is different in different fluids. Second thing we talked about was laminar, talked about laminar versus turbulent. Okay, and what did we see? Some of the characteristics that we saw of laminar flow versus turbulent flow: layer like, put some gap, layer like versus um, highly agitated. We saw vortices forming. We saw that it mixes quickly, random if you like. It's not completely random, random like. So layer like is the right. One more thing we saw: reversible versus irreversible. What else did we see? Another thing we saw, you recall? We saw about deformation, how deformation happens, how it looks like in the laminar flow, and how the deformation looks like in the turbulent flows. Much more deformation happens. And then we said Reynolds number. We yet don't know what is Reynolds number, but we have said that Reynolds number can be used to characterize turbulent flow. So high Reynolds number. Okay. So we can see, because we saw that Reynolds number allowed us to characterize. We don't know how to calculate that Reynolds number, nor do we know why we calculate Reynolds number. But we will see all these things as we go along. Another thing that we saw was different fluids behave differently. So water versus other kinds of fluids. We saw tubeless siphon. That doesn't happen with water, but it happens with other liquids, other kinds of liquids. We saw rod climbing. That doesn't happen with water. In fact, a vortex is formed with water. Walking on water, walking on fluid. Right? If you try to walk on water, obviously you will fall inside and get wet. But some other fluids are there on which we can easily walk, and not just we, children, everybody can walk and have fun with that fluid. So these are some of the properties of the fluid, other fluids, and we'll see what properties are there that makes all these things happen. And all these are phenomena not just important for having fun, but they are useful in application. So for example, rod climbing, if you see, when you are trying to process polymers, you are trying to make a film of polymer, or you're trying to make a bucket out of polymer and things like that, you need to make fluid, you need to make that polymer flow through different equipment, and then you can see that these different phenomena need to be considered for us to be able to design that that equipment or that process. This brings us to the next important part of the course, next important part of the lecture is what are the course contents. As I told you in the beginning, we are going to look at momentum transfer, which means, in short, if you like, fluid flow. And second thing we are going to look at is mass transfer. As mass transfer. When we are dealing with flow of fluids, what we are going to see first thing that we are going to look at is fluids. Increase the size. Fluids which are stationary. Okay. What happens in stationary fluids, and what are the different forces that are there in stationary fluids, and why we need to consider that. Okay, that's one. Second thing we are going to look at is fluids which are moving. And a better word for that is fluid dynamics. Dynamics means moving. So we are going to look at fluids which are moving. In this moving fluids, we are going to look at different things. Okay. The first thing we are going to look at is what are the different forces that are present. Let's move this a little bit. First thing that we are going to look at is we are going to deal with this flow of fluids in two ways. One is we are going to look at a macroscopic picture, the big picture, meaning the objects that we are going to talk about, or the forces that we are going to talk about, are over large scales, over the size of the object. So these are called as macroscopic situations. And then in macroscopic situations, we are going to talk about different things. One of the things that we are going to talk about is forces. What forces are there on macroscopic objects like ball, car, bus, uh, people, agitators, mixers, particles, and so on and so forth. Macroscopic situation. Macroscopic would mean that we are talking about sizes which are of the order of microns onwards, right? It is so micron is still a small, but it is still considered as a macroscopic. We'll talk about the reason why we are saying macroscopic. Then we are going to talk about energy and work and power. Okay. And then third thing that we are going to do, and the next thing that we are going to do in this macroscopic balances, after the macroscopic balances, we are going to talk about microscopic balances, macroscopic situations. And the microscopic situations we will talk about much later. Essentially, if you would like to categorize large scale phenomena versus small scale phenomena. Okay. And as you go along, we will see all these. And even when we start talking about mass transfer, we will talk about mass transfer from two angles: macroscopic angle and a microscopic angle. Okay. So this is what we are going to do. Immediate thing that we are going to do is start with stationary fluids, or fluids which are not moving, and why we need to consider, and what are the considerations that come up in these kinds of situations. So I told you that in this course we are going to talk about flow of fluids. One of the important parts that we as chemical engineers have to deal with is transporting fluids from one location to another location. That's what we are going to look at in this course for some time. Imagine that you have to take water from, let's say, ground floor of your building to, let's say, top floor of your building. What are the different ways in which you can take this water from ground floor to top floor? Can you think of some? One way could be fill that water in a bucket, carry the bucket, climb the stairs, carry the bucket to the top floor, use that water, go down, get another bucket, use that, get another bucket, use that, and so on and so forth. Do you think that's a good idea? Obviously not, because you have to do many trips. You'll spend a lot of energy. You just get tired carrying water rather than using that water for some other purpose. Could be a better way. One way could be, oh, we'll tie a pulley at the top. We'll have a rope. We'll tie the bucket to that rope. Put the lower the rope. Fill the bucket with water. Pull it up. Use it. Put it down. Fill it up. Pull it up. Put it down. Pull it up. Pull it up, and so on and so forth. Right? That could be one more way. Much more efficient. Much less time required. Much less energy required. Can you think of some more? One more could be, well, I put a pump at the ground floor, connect that to the source of water, just switch on the pump and transport the pump, put a pipeline, the pump will just transport that water through the pipeline to the top floor where we require. Three different situations, three different ways of taking water from ground floor to first floor or top floor. Climbing stairs, rope, pump. To transport same amount of water, what is different? We have utilized different equipment. We have utilized different geometry of carrying the water up. And that different geometry has meant that we will require different amounts of energy. Obviously, the most efficient is transporting water by pipeline in a pump, using a pump, right? Much less energy required. So whole throughout this course, that's a central phenomena, central dogma with which we are going to work, is how to transport fluid at a certain rate, at a required rate, from one location to another location. What geometry will I use for doing that, and how much energy am I going to require for doing that? So as I said, we are going to look at different things that are required. What is required? Flow is required of fluid, or transport of fluid from one location to another location. What can we do? We can do this in different ways: bucket, rope and bucket, pump. So equipment or geometry used for transport. That's the second thing. Third thing we said is the energy that is required, or power that is utilized in transporting the fluid at a certain rate through an equipment. So these three things are integral to each other, and throughout this course the geometry that I use dictates how much energy I require, how much power I require. How much fluid is to be transported decides how much energy is required. Depending on what flow rate or fluid I want, I should choose a particular equipment. If I have to just transport 5 ml of water, I won't put a pump. I'll just go down and get it up in a cup. But if I have to transport 100 meter cube of water in a day, I can't do it in bucket. I have to have a pump for transporting fluid. So the geometry that we choose is dependent on what flow I want and how much energy I will require. So these three things we are going to talk about again and again throughout this course. That's the central portion, central dogma, or central uh, uh, point of discussion of our of our uh, of our course.